Hi everyone, I'm Yuxing from Peking University. Today I'll be presenting Iceberg, a framework for automatically verifying DNS authoritative engines using just-in-time summarization. Let me start with some context. DNS is one of the most critical pieces of internet infrastructure. Every time you visit a website, send an email, or connect to any online service, a DNS lookup happens first. At the heart of DNS are authoritative engines, the software that answers queries by looking up records in configured zones. And when these engines have bugs, the consequences are severe. I believe most of us remembered that just last October, a latent bug in AWS DNS management system produced an incorrect empty DNS record, which cascaded into a 15-hour outage, taking on DynamoDB, NLB, EC2, and basically a large part of the internet with it. Similar outages have occurred over the years at Facebook, Google, Slack, and others. This shows that DNS engine bugs aren't hypothetical risks. So why is it so hard to get these engines right? There are three reasons. First, the DNS protocol is complex. There are dozens of RFCs governing how to handle different record types, wildcards, redirections, glue records, and their interactions. A correct engine must handle all of these combinations. Second, the implementations are large and diverse. We're talking about 2K to 10K lines of core logic written in Go, C, C++, or Rust, each with different data structures and design choices. Third, traditional testing is fundamentally limited. DNS engines take a zone configuration and a query as input, and the space of possible combinations is enormous. As a bit of a teaser, we will see that even state-of-the-art test generators like Scale only found 2 of the 12 bugs we eventually discovered. Now, formal verification offers a way out. So instead of testing with example inputs, verification proves that the engine behaves correctly for all possible inputs. For large software, the standard approach is to break the program into layers, model each layer with its own specification, and prove correctness against the spec layer by layer. This is what we call the refinement-proof approach. But here's the problem. This traditionally requires a lot of manual work. Someone has to design these layers, decide what gets simplified and how, and write specs for each one. In our prior work, DNS-V, published at SOSP 2023, we built a verification framework for an in-production DNS engine at Alibaba Cloud. The figure here shows the layered structure from DNS-V. DNS-V uses a refinement approach, which I'll call ahead-of-time summarization. So for higher-level modules with cleaner behavior, the blue ones, we use symbolic execution to automatically produce code summaries, which also serve as specifications like shown here. But this only works when we've already manually abstracted the low-level modules underneath. For those, the orange boxes, things like byte manipulation, data structure traversals, and memory management, we still needed handwritten specifications to hide the messy details. And that manual effort is the bottleneck. When we tried to apply DNS-V's approach to other open-source engines, the situation got worse. In Byte 9, the most widely deployed DNS engine, we estimated that 64% of functions would need manual specifications, amounting to thousands of lines of code. For Core DNS, 38%, for Power DNS, 44%. And what's worse, writing these specifications requires deep expertise in both formal methods and the specific engine implementation. We estimate that it takes months of work per engine, and the specs can break when the code changes. This does not scale. So, verification gives us correctness guarantees, but the manual effort is prohibitive. Can we get both? This is what we set out to achieve with Iceberg, an automated verification framework for DNS engines with low manual effort. To do this, we introduced the approach called just-in-time summarization. The key insight behind JIT summarization comes from how DNS engines actually operate. An engine always works with configured zones, which are concrete sets of domain names and records, like shown here. So when a query arrives, the engine traverses the zone data for a response. This means that zone data propagates through the code as invariants, such as fixed function arguments, constant memory contents, and bounded data structures. And these invariants can dramatically simplify what we need to summarize for a given piece of code, which in turn simplifies verification. Let me make this concrete with an example. So here is a simplified version of how bind compares two domain names. Now, domain names in the RFC format are stored as byte arrays with offset tables, as shown here. As we can see, this is very much low-level and performance-optimized code. Now, summarizing this function in general would be very hard. So the loop count here depends on the name length, and the memory accesses depend on the offset array, and there are many interleaving paths. But if we know that one of these names, say N1, the in-zone name, is actually a concrete name, like just example.com, then a lot of this complexity vanishes. We know now that the loop count is bounded to 3, and the memory accesses resolve to constants, and the function essentially just becomes compare the query name against this specific string. This is the core difference between ahead-of-time and just-in-time summarization. Ahead-of-time summarization must account for all possible inputs and all possible code paths, just in case. So many of those paths indicated by the white area here are unreachable in practice because of zone invariants. But the summarizer doesn't know that, and it ends up creating unmanageably big summaries, so we have to resort to manual specs. On the other hand, just-in-time summarization builds summaries on demand in the context where a function is actually called, indicated by the blue area. Because zone data flows into the function as concrete values, JIT can prune impossible paths and simplify the rest. We summarize only what matters, and the process becomes more automated. So how does Iceberg actually build these summaries? It performs symbolic execution on the LLV and IR of the target engine, starting from the entry point. As it walks the code and encounters function calls, it builds summaries for them on the fly, with zone invariants in hand. Let's go back to our name comparison example. So when the engine calls this function to compare the query name against example.com, Iceberg sees that one argument, say N2, points to concrete zone data. At the point where the code dereferenced a pointer into this data, say reading the label count, Iceberg splits the execution state. So instead of assuming the value of L to be symbolic, which will then produce an AOT summary, it uses the concrete value and continues. This is what we call state splitting. The effect is that the loop count unrolls to exactly 3 iterations. Memory accesses become constant lookups, and the summary for this call becomes more compact. In general, Iceberg splits whenever a symbolic value is used as a pointer dereference or an array index. Our paper has the full details here, but the key point is that these splits are triggered by zone data flowing through code automatically, and they happen just in time. Now, the engine doesn't just compare against one name, it might do this multiple times. The first time it calls the comparison function with example.com, Iceberg builds a summary. Here on the right, you can see what the summary looks like internally. It's a tree of constraints and effects. The specialized node here captures the zone invariant, and underneath are the possible outcomes. Now, the next time we encounter calls with the same domain, Iceberg can apply the summary directly, achieving refinement. But when called with a different domain, the existing context node doesn't match. So Iceberg re-summarizes the function with this new concrete name data and merges a new branch into the tree. Over the time, the summary grows to cover exactly the in-zone names the engine actually encounters. Now, under the hood, Iceberg represents summaries as trees of constraints and effects and manages them through 2 core algorithms, build summary and apply summary, which does what we just described, but more formally. Further, these algorithms also operate on a unified state and memory model that spans all proof layers, which I don't have time to cover today. You can check out our paper for the full picture here. Beyond the core algorithms, we also implemented 3 more techniques to really scale JIT summaries to full system verification. First, symbolic regions. This decouples summaries from concrete memory addresses. When a function takes a pointer to a stack allocated variable, the summary shouldn't be tied to that specific memory location. We replace concrete pointers with abstract region IDs, making summaries reusable across all call sites. Second, summary optimization. We design and run passes that remove redundant constraints and merge identical branches, similar to compiler passes, but for summaries. These greatly improve verification performance. And third, stub functions. We provide a lightweight interposition mechanism where users can hint invariants or force state splitting. This is the main mechanism to customize the summarization process. Putting it all together, here's the Iceberg workflow. The user provides a top-level specification of correct DNS behavior, the engine source code compiled to LLVM-IR, the stub functions, and a memory dump of the zone configuration, basically the memory state at the start of a query. Iceberg then runs push-button verification with no per-layer specifications needed. The output is either a summary confirming that the engine confirms to the spec, or a counterexample path revealing a bug. We implement Iceberg in Rust in about 16,000 lines of code using the D3 SMT solver for symbolic reasoning. We applied Iceberg to 4 major open-source DNS engines: Core DNS in Go, Bind in C, Power DNS in C++, and Hickory DNS in Rust. Our effort is illustrated in this figure. The blue boxes are code modules verified automatically by JIT summarization. The yellow box on top is the shared reference spec, and the yellow triangles indicate manual stub functions. Now we focus on verifying the core lookup logic, that is matching a query to zone records and composing the response. I/O, networking, concurrency, and other peripheral features are out of scope. For the top-level spec, we derive a DNS reference model from a collection of RFCs covering the core resolution algorithm. Since the engines don't all cover every RFC, we tailor the spec slightly for each engine's documented behavior. Let me highlight 2 aspects of our verification experience that show how JIT summarization handles real-world complexity. First, data structures. The 4 engines use very different structures to organize zone data. We have red-black tree, B trees, hash tables, and multi-index containers. With manual specs, you would have to understand each one intimately and write abstractions tailored to it. JIT summarization, on the other hand, sidesteps this entirely. Since the zones are invariants, state splitting adapts to the concrete data layout. The same mechanism handles all 4 with no per-data structure specs needed. Second, language-specific IR patterns. For example, Power DNS uses C++ exceptions as part of normal control flow, and Hickory DNS is async Rust. Both produce complex IR patterns, but for Iceberg, JIT summarization just handles the compiled IR as any other code, exploring only the reachable states during symbolic execution. No manual modeling of exception stacks or async control flow was needed. Now, for evaluation, we verified each engine against 3 categories of zones, including simple zones with 2 to 4 records, complex zones with 10 to 12 records, and 2 real production zones from the public CZDS database. We compare against Scale, the state-of-the-art symbolic test generator for DNS engines published at NSDI 2022. We measure 3 aspects: bugs found, manual effort, and verification overhead. For bugs, we found 12 new ones across 4 engines, 8 in Core DNS, 2 in Power DNS, and 2 in Hickory DNS. These contain critical bugs like wrong response codes or missing answer records. In comparison, Scale only caught 2 of these 12 using the same zones. Further, some of the bugs, like the 6th one, were actually caused by incomplete fixes for issues Scale had previously reported. Testing found the original bug in 2020, and the developers thought they fixed it and closed the issue. But verification later here revealed a new trigger for the same bug, showing that the fix was incomplete. This demonstrates Iceberg's superior correctness guarantee. In terms of manual effort, Iceberg stays low across all engines. The spec-to-code ratio ranges from 5.8% for Power DNS to 9.6% for Core DNS. Upfront porting takes about 1 person week, and subsequent version retrofitting takes as little as 1 person hour. As for verification overhead, it scales linearly with zone size. Minutes for simple zones, about half an hour for complex zones, and a few hours for production zones with hundreds of records. All runs terminated with reasonable time on a standard cloud server. Now, stepping back, we believe the core idea of Iceberg actually extends beyond DNS. Many systems operate on pre-configured data. Network switches have forwarding tables, SDN controllers have flow tables, and database query engines have schemas and indexes. Generally speaking, whenever a system's behavior is shaped by such fixed configuration, JIT summarization can exploit those invariants to make verification tractable. To summarize, Iceberg uses just-in-time summarization to automatically verify DNS authoritative engines. By leveraging zone data as invariants, we eliminate most manual specification effort while maintaining correctness guarantees. We verified 4 engines, found 12 new bugs, and kept manual effort low. Thank you for listening. I'm happy to take questions now.